we can interpret the real and imaginary parts of a complex number as x and y coordinates. Thus, we can interpret a complex number as a point in the plane. And in this context, we'd call it the complex plane. So here, the complex number z is represented as a point. Its x-coordinate is its real part, and its y-coordinate is its imaginary part. Now I'll illustrate the idea of complex numbers as points in the complex plane by plotting some complex numbers. I'll import a plotting procedure we provide and plot this list of numbers. Let's plot a longer list of complex numbers, one derived from an image. I'll first import some image manipulation procedures defined in a module we provide. And now load an image. Now we find the length of this list, which is the number of rows, and the length of one of its elements, which is the number of columns. And now we'll define a collection of complex numbers based on the intensities of the pixels in the image and plot that. The plot function takes an optional second argument giving the scale of the plot and an optional third argument giving the size in pixels of the points displayed. Once we've interpreted complex numbers as points in the plane, we can take advantage of geometric properties like length and distance. So we define the absolute value of a complex number to be the length of the line segment between that complex number, represented as a point, and the origin. That is, it's the distance between that point and the origin. In math, we would write it with vertical bars, and in Python, the absolute value of a complex number is written abs of complex number z. Now here's a function. It maps the input complex number to that number plus 1 plus 2i. How do we interpret that geometrically? The effect of this function is to add 1 to the real part of z and 2 to the imaginary part of z. We can think of that as operating on a point and getting another point that's 1 unit to the right and 2 units up. So applying that function to all these points would shift them up and to the right. We call a function of this form a translation. It's said to translate a set of points. Let's use Python to translate these points in L. We can similarly translate the points from the image. Take this image, translate them so that the image is centered at the origin. Given the input, it adds a complex number z0 to the input. And a translation can move the picture anywhere in the complex plane. All right, so we can interpret the complex number z0 as representing the translation that adds z0 to the input. Once we interpret a complex number as a translation, we can think of it as an arrow in the complex plane. The arrow's tail can be located at any point z. Then the arrow's head is located at z plus z0. So the arrow shows an example of how the translation acts on a point. So let's try representing this complex number as an arrow. We can choose anywhere to put its tail, and one convenient place to put it is at the origin. So the tail will be here. And the head should be at the location with x-coordinate -6 and y-coordinate 5. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So the head should be here. So the arrow would look like that. Now, consider two complex numbers. Each of them corresponds to a translation. Let's take the functional composition of those two translations. So first we apply f2 to the input, then we apply f1. That's the same as adding first z2 and then z1. So we can represent functional composition by adding arrows. Here's an example. Let's say we're first going to apply f2. So that takes a point. Let's start with the origin. And translates it 3 units to the right and 1 unit up. 1, 2, 3, 1. So that goes here. Next, we'll write down the arrow representing this complex number. This complex number says move 2 units to the right and 3 units up. Now we can write it as an arrow with the tail located anywhere, and a convenient place to put the tail is at the head of the last arrow. So we're going to put it right here. Here's the tail. The head will be 2 units to the right and 3 units up. So this arrow is represented, this complex number is represented by this arrow. Now, what about the functional composition? The functional composition adds z1 plus z2 to its input. We can find that arrow by choosing its tail to be the tail of the first arrow and its head to be the head of the second arrow. So z1 plus z2 is represented by this arrow. So we see that addition of complex numbers can be represented by putting arrows together, adding them in this way. Consider the operation of multiplying a complex number by 0.5. What's the geometric interpretation? How does this affect arrows representing complex numbers? So we're applying the function f of z equals 0.5 times z. Let's say we start with the complex number 2 plus 4i. We represent that by an arrow that moves 2 units to the right and 1, 2, 3, 4 units up. So this arrow. When we multiply the complex number by 0.5, what we're doing is multiplying the real part by 0.5, halving the real part, and halving the imaginary part. As a consequence, the arrow representing that complex number goes 1 unit to the right and 2 units up. It gives you an arrow in the same direction, but half the length. This is called scaling. Let's see what it looks like when we scale all the complex numbers in the list L and plot them. Or the numbers in the list M derived from the image. What about if we multiply a complex number by -1? Let's try that. Let's start with the same complex number, 2 plus 4i. Multiplying this by -1 means multiplying the real part by -1 and the imaginary part by -1. So we end up with -2 plus -4i, which is an arrow that goes in exactly the opposite direction. Now we'll multiply each of the points in the list L by -1 and plot the result. And the same for the points in the list M. How would we rotate by 90 degrees? Let's say we start with the complex number 2 plus 4i. So that's represented by the arrow that goes 1, 2, 3, 4. Rotating that 90 degrees should give us this arrow, represented by the arrow that goes 4 units to the left and 2 units up. This is the complex number 2 plus 4i. This is the complex number minus 4 plus 2i. So we need a way of mapping from the complex number x plus yi to the complex number minus y plus xi. How can we do that? We use the property of I, that I squared is minus 1. So we multiply I times x plus yi. Using the distributive law, we get x times I plus y times I squared, which is x times I minus y. So the function we use for rotating by 90 degrees is f of z equals I times z. What about rotating by another angle? Well, let's start with this definition. The argument of a complex number is the angle measured in radians between the x-axis and the arrow representing the complex number. To see how to increase the argument of a complex number, we turn to a formula due to Euler, a remarkable mathematician who contributed to many areas of mathematics, not to mention music theory and cartography. Euler's formula states that for any real number theta, e to the theta times I is the point z in the complex plane on the unit circle whose argument is theta. Here, e is the famous transcendental number 2.71828 and so on. So here's an example. We plug in theta equals pi over 4, which corresponds to 45 degrees. E to the I times pi over 4 is this point in the complex plane. Notice that the arrow to that point forms a 45-degree angle with the x-axis. If we plug in theta equals pi, that corresponds to an angle of 180 degrees. So the complex number is this one, which turns out to be minus 1. So e to the I times pi is minus 1. Let's form a bunch of complex numbers by plugging in multiples of 2 pi over 20 for theta in Euler's formula. First we have to get pi and e. Now, forms a circle of dots. Next, let's try multiplying all these complex numbers by 2. Let's see how we can use the Euler's formula to rotate points by any angle tau. Any complex number can be written in this form. Z equals r times e to the theta I, where r is a real number, which is the absolute value of z, and theta is the argument of z. What we want to do is increase the argument of z. We'll use the exponentiation law. E to the a times e to the b is e to the a plus b. So if we start with the complex number z, which is r times e to the theta I, and we multiply it by e to the tau I, by the exponentiation law, that's the same as r times e to the theta I plus tau I, which is the same as r times e to the theta plus tau I. So we get a complex number whose absolute value is the same as the one we started with, but whose argument is theta plus tau. So the function that multiplies by e to the tau times I carries out rotation by an angle of tau. To illustrate this, we'll rotate all the complex numbers in the list L by pi over 4 radians, basically 1/8 of the circle, which is equivalent to 45 degrees. and the same for the complex numbers in the list M.